Hey everyone, welcome to the third session of Geometry and Tacos on hyperkähler geometry. Let me start by just thanking the organizers for putting this together and for the invitation. It's a pleasure to speak. All right, now let me just take 1 second. Okay, so I am going to be talking about some recent work with Henri Guanancia and Kristen Lane on the BBDGGHKP decomposition theorem for non-projective Calabi-Yau varieties. If you don't know what that is, then hopefully that'll become clear very soon. So let me start with the definition you will surely see many times this session, namely that of a holomorphic symplectic manifold. So we say that a compact Kähler manifold M is holomorphic symplectic if it admits a two-form that is everywhere non-degenerate. So the simplest examples of these are provided for by complex tori. So if we take, for instance, a two-dimensional complex torus, then take your favorite non-zero two-form, which is translation invariant. This will descend to a non-zero two-form downstairs, which is therefore non-degenerate. But of course, I can do the same thing, with a four-dimensional torus, or indeed any even-dimensional torus, by taking, for instance, something like this. Basically, your favorite non-degenerate symplectic form. Okay, so another important example is if I take a two-dimensional torus, then I can take the Hilbert scheme of points of length n subschemes on A, and this is also a holomorphic symplectic manifold. Now, we furthermore say that M is irreducible holomorphic symplectic if it's simply connected and it has basically one holomorphic two-form, namely the non-degenerate one. Okay, so obviously the Hilbert scheme of points will not give us an example of an irreducible holomorphic symplectic manifold because it is not simply connected. But if we take a K3 surface S, then the Hilbert scheme of n points on that is an irreducible holomorphic symplectic manifold. Now, irreducible holomorphic symplectic manifolds are important because they form one of the three main building blocks for Calabi-Yau manifolds. And this is where the Beauville-Bogomolov decomposition theorem comes in. So the theorem says that if M is a compact Kähler manifold with numerically trivial first-term class, then possibly after a finite étale cover, it splits into a product of three sorts of special Calabi-Yau varieties. Namely, there's a torus factor, there are factors that are irreducible holomorphic symplectic, and then there are factors that are called irreducible Calabi-Yau, which means that they are simply connected and their only holomorphic form is a top-dimensional form. Okay, so just as a very simple example, we saw in the last slide that the Hilbert scheme of n points on a two-dimensional complex torus is not irreducible holomorphic symplectic because it's not simply connected. But if we look at the sum map, which just adds together the support of my length n subscheme, then it will split over the étale cover given by multiplication by n. Basically because, if we base change along this étale cover, that allows me, that's equivalent to choosing a midpoint for the subscheme. And once I choose a midpoint, then I can sort of recenter it at 0. And so the base change will split into a copy of A parametrizing where the midpoint is, and then the variety parametrizing length head subschemes that are centered at 0. And it turns out this is irreducible holomorphic symplectic because we've killed the fundamental group. Okay, so this forms the second infinite class of irreducible holomorphic symplectic varieties, the generalized Kummer's. So let me, because it'll be important later on, let me give just a brief idea of some of the tools that go into proving this theorem. So we first need to show the splitting. And that first comes from the fact that there's a particularly nice metric on a Calabi-Yau manifold, namely the Ricci flat metric. And once I have this nice metric, then I can use some strong results from Riemannian geometry that tell me that as soon as the holonomy group splits, then the manifold splits. Okay, so if you're not familiar with what holonomy means, basically, if I have a Riemannian manifold and I start at a point and I take a tangent vector, then for any path, I can sort of parallel translate that vector around, and maybe I end up with some other vector. In particular, by parallel translation around this path, I get an orthogonal transformation of the tangent space at that point. And the group I get by all such parallel translation operators around loops is called the holonomy group. Okay. And so these theorems from Riemannian geometry tell you that if this holonomy group splits, then in fact the manifold has to actually split into factors. And this also explains where why the étale cover might be necessary. Sort of the holonomy group, by general theory, is compact, but it might have more than one component, and so the étale cover is to make the holonomy group connected, and then once it's connected, just by sort of Lie group theory, it has to break into a product. So that will give us a splitting into Riemannian manifolds with certain holonomy properties. And then the next step is to actually understand the pieces that show up and say something about them. So the first step of this is a classification of which holonomy groups show up. And there's basically, in this case, 3 that shows up. There's the trivial group, there's the symplectic group, and there's the special unitary group. And second, we have to relate these 3 holonomy groups to the holomorphic geometry. And this is via the Bakker principle, which basically says that any holonomy invariant is the same as giving a global holomorphic form. Okay, so just to be very concrete, if I write down these 3 possible holonomy groups, then in the case where there's no holonomy, namely if I have a flat structure, then this is going to end up giving me a torus. In the symplectic case, the group theory gives me a 2-form invariant, namely the symplectic form, and therefore that gives me a holomorphic symplectic form. And on the special unitary side, basically the only invariant is a top-dimensional form, and this is what gives me the irreducible holomorphic symplectic. The irreducible Calabi-Yau guys. Great. Now let's talk about the singular case. And before we talk about the singular case, let me say a few words about why we're talking about the singular case. The first reason is that they're basically unavoidable when you're doing sort of higher dimensional geometry. Singular Calabi-Yau varieties naturally show up even if you're only interested in the geometry of Calabi-Yau manifolds. So for instance, if we run the MMP, then we know that certain mildly singular varieties are produced. Or when we're just in general doing birational geometry of Calabi-Yau varieties, I may produce singular objects. Also, when I study degenerations of Calabi-Yau varieties, certain mild degenerations will produce singular Calabi-Yau varieties. Or if I'm taking group quotients, that's another easy way to produce singular Calabi-Yau varieties. And lastly, and this is mostly in the symplectic case, if I form moduli spaces, then a lot of the times I'll produce a singular, in that case, symplectic variety. Okay, so the first reason to study them is because we can't avoid them. Second reason is that actually at least in the symplectic case, the theory of singular symplectic varieties is basically as nice as the smooth case. In fact, many of the sort of hallmark results from the manifold case generalize almost exactly to the singular case. So for instance, we have this extra piece of structure on the second cohomology in the case of singular symplectic varieties, namely the Beauville-Bogomolov-Fujiki form. And turns out that deformations are unobstructed, and that I have a local Torelli theorem, which is governed by the H2. And in fact, I have a global Torelli theorem, again, by looking at the period on H2, just as in the smooth case. And maybe finally, again, this is specific to the symplectic case, another reason to study symplectic varieties is, one of the main problems in the manifold theory is that there's not so many examples of irreducible holomorphic symplectic manifolds. We know sort of two infinite series, the Hilbert scheme of points on a K3 and the generalized Kummer, and then two sporadic cases due to O'Grady. But in the singular case, it's actually fairly easy to produce more deformation classes of symplectic varieties. Okay, so let me give a precise definition for what a symplectic variety is. This is a definition that goes back to Beauville. Say that a compact, normal, Kähler complex space with rational singularities is symplectic if on its regular locus it admits a nowhere degenerate holomorphic two form. Okay, so a couple comments about this definition. First, the precise definition of what it means to be a Kähler complex space is a bit complicated. You should think of it as saying that it has an object which locally, if I embed x into Cn, is the restriction of a Kähler form. Of course, in the projective case, we can just say that it's a projective variety. And second, I should point out that this is not the definition as Beauville originally gave it. He sort of imposed canonical singularities. So here I'm using some more recent some recent results of Kebekus and Schnell, which says that in the presence of a top form, rational singularities imply canonical singularities. Okay, so this is sort of the analog of what symplectic manifold is in the singular case. And so now we might ask, what is the analog of an irreducible holomorphic symplectic manifold? And that's a bit tricky. So remember, in the smooth case, we require a simply connected and that there's one two form. And basically it's tricky because as we said, in some sense, the fundamental group of it's sort of a tricky relationship between the fundamental group of x and its regular part is basically the issue. So the correct definition here is that x is an irreducible symplectic variety if, first of all, if I look at sort of the algebra of forms on the regular locus, that it's generated by this nowhere degenerate holomorphic two form, but moreover that also remains true on any finite quasi-étale cover. Okay, so a finite quasi-étale cover is just a finite map which is étale on the regular locus. And it turns out that these are the correct sort of symplectic building blocks for the generalization of the Beauville-Bogomolov decomposition to the singular case. Okay, so before I state that theorem precisely, let me give a few examples. So as I said, sort of symplectic varieties are preserved under taking quotients, group quotients. So for instance, if you take a symplectic variety X, then the nth symmetric product is always a symplectic variety. Or for instance, the singular Kummer surface, if you take a two-dimensional complex torus modulo plus minus 1, this is a symplectic variety. It is not irreducible symplectic. So this is an important example to keep in mind. I mean, the map from the quotient map, the map from the torus to the torus mod plus minus 1 is quasi-étale. And whereas, sort of the algebra of forms down here looks like an irreducible symplectic variety, namely there are no one forms and there's a unique two form. Once I go up to A, now I suddenly have one forms. So this is not an irreducible symplectic variety. Second, birational contractions of symplectic varieties are still symplectic varieties, kind of obviously, because the definition is in terms of the existence of a certain kind of two form on the regular part. And lastly, and I mentioned this before, that moduli spaces of sheaves on K3 surfaces produce symplectic varieties. So provided the Mukai vector is primitive and the polarization is generic, you will get a smooth symplectic manifold, but if either of those fails, you will easily produce a singular symplectic variety. Okay, so now let me state the singular version of the Beauville-Bogomolov decomposition theorem. And this is the BBDGGHKP theorem. This is the sort of culmination of many years of work of Drouel, Greb, Quinancia, Höring, Kebekus, and Peternel. And the theorem says the following: if X is a projective variety with log terminal singularities and vanishing first Chern class, then we have a decomposition into three sorts of pieces. And the three sorts of pieces are strongly analogous to the smooth case. We have complex tori that show up. We also have irreducible symplectic varieties in the sense of the slide before the last one. And finally, we have what we might call irreducible Calabi-Yau pieces, and this is sort of the analog of the Calabi-Yau condition in the singular case, namely that we say that C is irreducible Calabi-Yau if its algebra of forms on its regular part is generated just by a top form. So it only has a top form, and also that remains true whenever I go to any quasi-Attell cover. Let me just note here that because the singularities are log terminal, in particular, the canonical class is Q-Cartier. So it makes sense to talk about the first Chern class of X inside rational cohomology. So important for this talk is the fact that now, in the smooth case, we were just talking about Kähler manifolds. But here we have to assume that X is projective. And that is because there are certain parts of the proof that require that sort of the techniques coming from the smooth case do not generalize to the singular case, and we have to take some algebraic input instead. So let me just go through the basic ideas. So once again, we first have to get the splitting. And this starts off sort of similar to the smooth case. We use the fact that there is a particularly nice metric, namely a Ricci flat metric on the regular part. The issue now, however, is that this metric will not be complete. And so some of the techniques of coming from Riemannian geometry start failing. The good news, however, is that by analyzing the holonomy with respect to this metric, we still get a splitting on the level of foliations. In other words, we may not get a splitting of X into spaces, but the tangent bundle sort of decomposes in a way that was very analogous to the smooth case. And then, using some results on integrability of algebraic foliations, we can show that those foliations are integrable and therefore actually turn that splitting of the tangent bundle into foliations into a splitting of the variety into spaces. And once we have that, sort of the second step is to classify the factors, again, in terms of the holomorphic geometry. And this is once again by a Bakker principle, which says that the holonomy invariants are the sort of same as holomorphic forms on the regular part. So now, what about the non-projective case? So in order to follow this strategy sort of directly, one needs some replacement for these key places where algebraic techniques are used. Or one can do something different, and that's what we're going to do here. We're going to instead appeal to deformation theory. And the starting point is going to be the following theorem, namely that if X is a proper Kähler variety with log terminal singularities and vanishing first Chern class, then there is a locally trivial deformation over a smooth base in which projective fibers are analytically dense. Okay, so this is now sort of the idea is clear. If I know I have this, if I draw my family like this, and I know lots of the fibers are projective, And therefore, you know by this theorem that the fibers all have decomposition theorems. You could try to somehow get this to deform sideways and then get a decomposition on the special fiber. Okay, so there's a couple of things I should explain here. So first, I said it's a locally trivial deformation. This is actually pretty important for the whole story to work out. So let me say a few words about that. So locally trivial deformations are just what they sound like. We say that an analytic family is locally trivial if locally on the source it's the trivial map. Namely, there's some open set which I can sort of straighten out to an actual product map. Okay, now this is in the analytic category. In the algebraic category, it's not going to be true basically ever that you're locally trivial unless you're actually trivial, because algebraic open sets are just too big. But I can still make sense of this definition in terms of the completed local rings. In other words, we say a family is locally trivial if at each point the sort of completed local ring looks like it's coming from a trivial family. Let me just note, so for instance, the easiest example of a locally trivial family is a smooth family is automatically locally trivial. Okay, so locally trivial maps have a nice deformation theory. Sort of the locally trivial deformations of a space are governed by the tangent sheaf. And so the deformations are governed by the H1 of the tangent sheaf, which sits inside the full space of flat deformations, which is this X1 group. And the obstructions are governed by H2 of the tangent sheaf, which again sits inside the full obstruction space for flat deformations. And again, just getting back to my previous comment, if X is smooth, then this, in both cases, this is equality. So we sort of recover on the sort of deformation theory side that locally trivial deformations are the same as flat deformations for a smooth variety. I should say here that we're using sort of in a kind of a funny way characteristic zero here in order to describe the tension obstruction theory. Okay, so why are locally trivial deformations important? Well, if we want to sort of use deformation theory to understand these singular Calabi-Yau varieties, we in particular want to be able to produce deformations. And the way you do this in the smooth case is using the Bogomolov-Tian-Todorov theorem, which tells you that deformations are unobstructed, therefore exist when they should. And the proof of that is ultimately coming from sort of Hodge theory via T1 lifting. Sort of the key insight here is that the deformation space, if I'm talking about a Calabi-Yau manifold, because I'm Calabi-Yau, can be identified with a certain piece of a certain Hodge structure. And therefore, when I deform, it deforms as a vector bundle. And by T1 lifting, that's enough to get unobstructedness. Okay. So that's why locally trivial deformations are important to consider in the singular case, because locally trivial deformations are topologically locally trivial. In other words, there's an analog of a resonance theorem. So if I have a locally trivial family, it's a topologically trivial family. This is, of course, not true for flat families. For instance, if I have sort of a family of elliptic curves degenerating to a nodal curve, then this is obviously not topologically a bundle. So for us, this is good news, because if you're topologically a bundle, then that means that the singular cohomology groups sort of deform in a local system, and therefore I actually get a variation of Hodge structures in locally trivial families. Okay, so there's at least a chance of trying to prove some unobstructedness statement via T1 lifting. And indeed, there are certain cases in which one can show that for a Calabi-Yau variety X, the locally trivial deformations are smooth. The locally trivial deformation space is smooth. So for instance, for symplectic varieties, this is a theorem of Namikawa in some cases, and by me together with Lane in some other cases, in the general case. And I mean, so again, the sort of proof is by relating the deformation theory to Hodge theory. So in this case, you can show that using the symplectic form, that the first cohomology of the tangent sheaf is related to H1 of the sheaf of reflexive one forms, which in turn you can show is computing a certain piece of the Hodge structure. Therefore, you get unobstructedness by T1 lifting. Now, there's a bunch of isolated cases in which one can show that locally trivial deformations are unobstructed. But it's not clear at all, like whether this should be true in general. Let me just at least point out that it is not true that flat deformations of Calabi-Yau varieties are unobstructed. And this goes back to an example of Gross. So in order to get some kind of analog of the Bogomolov-Tian-Todorov theorem, it seems like you should be restricting to locally trivial deformations, but we still don't know whether certainly whether it is true, maybe even if it should be true in full generality for Calabi-Yau varieties. Okay, but then how do we prove the theorem, right? So again, the theorem is saying that for any proper Kähler variety with log terminal singularities and vanishing first turn class, that there is some locally how are we producing these deformations? There is some locally trivial family over a smooth base over which in which the projective fibers are dense. Okay, and this is often, for obvious reasons, called admitting a strong locally trivial approximation. Okay, well, here's the key idea. So we use the holonomy splitting to get a certain kind of decomposition of the tangent sheaf, where all of the two forms vanish on the P part, and the E part carries a nowhere degenerate holomorphic two form. Okay, so what is the reason for this? Well, sort of the idea is that we know that symplectic varieties have unobstructed deformations. We don't know about Calabi-Yaus in general, but if we can, if this splitting of the tangent bundle actually came from a splitting of the variety, then this guy would be symplectic and therefore would have unobstructed deformations. And this guy, since all the two forms are 0, this guy has H20 equal to 0. And that's important because sort of the obstruction to being algebraic is the existence of two forms. I mean, if we look at the H2 of Z, then it has three pieces, H20, H11, and H02. And we know that the Kähler cone is open inside H11. And as soon as we have a rational Kähler class, then we know by the Kodaira embedding theorem that we're projective. Okay, so if there is no H20 part to this Hodge structure, then that's automatic. Okay, so the motivation for considering a tangent bundle splitting of this form is that if it, we're actually coming from a splitting of X into factors, then this factor would be symplectic, and therefore have unobstructed deformations. This factor would be projective automatically. So we can deform X to a projective variety by just deforming the symplectic part. Because that's the key idea. So just to summarize, this sort of symplectic part E is entirely responsible for all of the non-algebraicness. And just as in the case of actual symplectic varieties, you can make sense of locally trivial deformations along E, which have deformation space H1E, and one can show by a similar argument as in the symplectic case that this deforms as a vector bundle, and therefore by T1 lifting, it produces a subspace of unobstructed deformations. So we're not showing that all locally trivial deformations are unobstructed. So this may well not be smooth, but there's some thing sitting inside it which is smooth and which is responsible for all the non-algebraicness. Okay, so let me just note that this is related to a conjecture of Piranel, which in general posits that every minimal proper Kähler variety should admit an algebraic approximation, meaning it should admit a flat family which specializes to that proper Kähler variety, and a sequence of points, the fibers over which are all projective and converging to the special point. So here we're doing more than that. In fact, instead of just producing a flat family, it's a locally trivial family. And instead of there just being a sequence of fibers that approaches zero that's projective, the sort of strong part here means, in fact, the projective fibers are analytically dense. Okay, so now I can state the second main theorem, which is just the decomposition theorem, but now in the non-projective case. So now let X be a proper Kähler variety, but otherwise the same. So it has log terminal singularities and vanishing first term class. Then once again, we claim that there, after a finite quasi-étale map, there is a splitting into three kinds of factors with the same identification of the factors. There's complex torus factors, there's irreducible symplectic factors, and irreducible Calabi-Yau factors. Okay, so let me spend the rest of the time just briefly describing some of the ideas that go into the proof of the second theorem. And let's start with a few observations. So consider this locally trivial deformation that we have now produced that has many projective fibers. So first, observe that, or whatever, maybe not observe this, but it's a fact that by work of Claudon, Graf, Guénancy, and Naumann, we can split off what will be the torus factor in the Beauville-Bogomolov decomposition. Okay, and this requires some argument, but essentially the point is that where does this torus come from? Well, we can take the Albanese in the analytic category, and so we can at least produce a torus that should be the sort of torus factor of the Beauville-Bogomolov splitting. The tricky part to prove is that when you take the Albanese, it actually accounts for the whole flat part of the splitting of the tangent sheaf into foliations, the Holonomy splitting. And this actually uses, this is something they do in their paper, and it uses the fact that the singularities sort of can be approximated by algebraic singularities. A second observation is that we can sort of spread out quasi-étale covers in locally trivial families. This is essentially because quasi-étale covers are topological in nature because they're just étale covers of the regular locus. So if I have a locally trivial deformation, then the sort of regular locus also deforms in a topologically constant way. And therefore, any quasi-étale cover of a fiber can be spread out to a quasi-étale cover of the entire family. And third, we're going to need this result of Quebecois-Schnell that I already quoted, namely that if X has rational singularities, which is true in this case, if we take a resolution of X by, say, Y, then the holomorphic forms on the regular part of X are computed by the global forms upstairs on the resolution Y. Okay, so the first step is to prove a lemma which says that any locally trivial family admits a simultaneous resolution. And this is definitely not true for flat families. Again, in the easiest possible case, you can consider, elliptic curves degenerating to a nodal rational curve. There can't be a simultaneous resolution because then I would have a family of elliptic curves that was specializing to a smooth rational curve, which can't happen. However, if we have a locally trivial family, it's at least plausible that I can sort of take a simultaneous resolution like that. Second, I should say that, okay, so this is the example I just mentioned. It's not the case that every resolution will deform sideways. Okay, and so again, just as a simple example, if we have a family of varieties like this, and suppose there's a curve or something in the special fiber that doesn't deform sideways, and suppose we blow that up. We take a resolution that blows that up, well then obviously that blow up can't deform sideways, and so that will give me a resolution that doesn't deform sideways. So the key point is that the functorial resolution is the one that you should ask to deform sideways, and that's the one that sort of only blows up what it has to. The idea in some sense is that if you have a blow up you must do, then if you in a locally trivial family, you also must do that blow up in every fiber because the singularities are all the same. Okay, so that's the idea. The actual proof of this lemma is by deformation theory, and the way the functorial resolution shows up is you see when you do the deformation theory that being able to deform the resolution is related to being able to lift tangent fields. Okay, so as an important corollary of this lemma, and using Chebyshka-Schnell, we get that the dimensions of the space of holomorphic forms on the regular loci is locally constant in locally trivial families. And this just follows from the fact that we know Hodge numbers are constant. So if we take a simultaneous resolution using Chebyshka-Schnell, this is the same as the dimension of forms on the resolution, and the resolution is moving in a smooth family. Okay, great. So with those observations in place, we can now prove the second main part of this argument, which is that if we have this locally trivial family, X over S, then there is some quasi-Étale cover of the whole family, which has a Beauville-Bogomolov decomposition for all the fibers in some Zariski open subset, possibly after a finite base change. Okay, so basically what this lemma is saying that remember in this family we have many projective fibers, and therefore on each projective fiber we know there is a quasi-Étale cover where we have a Beauville-Bogomolov decomposition, and this lemma is saying we can spread that decomposition out at least in a Zariski open subset. Okay, so what's the proof? Okay, well the first observation is that in this locally trivial family, if I look at all of the Beauville-Bogomolov decompositions I get everywhere where I know I have one, only irreducible holomorphic symplectic and Calabi-Yau factors can show up. Because remember, we sort of got rid of the flat part, and therefore, nowhere is there a flat part. And therefore, in the decomposition, there's no torus that ever shows up. Second observation, and this uses the corollary we just proved, is if one fiber is irreducible holomorphic symplectic or Calabi-Yau, then in fact all of the fibers are. And that's because, let me just go back to the corollary, that's from this corollary. Because we know that the holomorphic forms on the regular locus, the number of them is constant in locally trivial families, and the definitions of being irreducible symplectic or Calabi-Yau are in terms of how many holomorphic forms on the regular locus you have. So you can read off whether you have the correct number in one fiber from having it the same property on the other fiber. Third, if one fiber is a product, in fact, in a Euclidean open set of that point, all of the fibers are products. So where does this come from? This comes from the fact that, again, because there's no flat part, a product can only deform to a product. And this is from essentially a tangent space computation. The point is that if I look at the deformation space, locally trivial deformation space of a product, then by Kunith, this has a variety of pieces. This has a piece that's coming from deformations, deformations of Y, And then it also has a piece that's coming from deformations of Z. Okay, and so these two together are sort of responsible for the deformations where you stay a product. But then you might have some other factors. You might have an H1 OY tensor H0 TZ factor, and vice versa. You might have an whatever, H0 tangent bundle Y tensor H1 of OZ. Okay, so the point is that these don't show up. So these are the factors where you sort of twist the product structure, and these do indeed show up for tori, because for instance, you could take a product of elliptic curves and deform it to an abelian surface that's not a product of elliptic curves, and that's because of the fact that we have these infinitesimal automorphisms that we can twist by. But because we've eliminated the flat factor, this doesn't happen. So every deformation of a product without a flat factor is a product, and therefore in this family, if you have a product at one point, you have a product in a Euclidean open. And then by using the relative duodee space, you can show that in fact that once that product decomposition deforms in a small open set, it actually has to deform in a Zariski open set. Possibly after a finite base change. The finite base change basically comes from getting rid of the monodromy between the factors as you go around the special point. Okay, so now we can prove the lemma. Basically, the point is, in this locally trivial family, take a projective fiber on which you have some quasi-étale cover where you have a decomposition. Spread out that quasi-étale cover to the whole family. Take the decomposition and then spread out that decomposition. Okay, so this gives us a decomposition, at least on a Zariski open set. Okay, so that's pretty good news, especially because, again, using the duodee space, which is proper over S, it now makes sense to take the limit of the leaves that show up in the product decomposition over that Zariski open set. And so the main remaining problem is to understand that the limits of those leaves give you a product structure on the special fiber. Okay, so in other words, so let me just be a little more precise. So we started off with this family. We took some quasi-étale cover, which at least on some open looked like a product of a bunch of stuff. And at this point, we may as well assume that our base is a disk, and the Zariski open is just a punctured disk. And so now we would like to say, so let's for simplicity just assume that there's two factors in this decomposition. There's a Y and a Z, where these are families over U. And so now we would like to say, okay, well, take the cycles of that look like fibers. So something that looks like this. Okay, so this is for t not equal to 0. And take the limit as t goes to 0. And this gives me some, let me call it, let me call it F. This gives me some limit cycle inside the special fiber x0. Okay, and we can do the same thing for the fibers in the other direction. Limit maybe like G, which is also contained in here. And the question is, under what circumstances, if I look at all of those limit leaves, do they actually give us a sort of product structure on the special fiber? Okay, so what could possibly go wrong? Well, two things could go wrong. When we take the limits of these leaves, they could break into components. They could become either reducible or non-reduced. Or they could intersect. If they define a product decomposition, then they better only ever intersect once. So the sort of enemy is that whereas over t not equal to 0, sort of my leaves look like this. This could degenerate to a situation where maybe one leaf sort of breaks into a component like this, and the other leaf sort of breaks into a sort of shares a component, the first guy. Okay, so how do we rule this out? Okay, well, the first observation is that in this locally trivial family, we know that generically the family splits, and therefore in terms of the Hodge theory of cohomology, that also splits. Sort of, there's a Kunith decomposition of Hodge structures away from the special fiber, and because this is a locally trivial family, that implies that there must also be a splitting as Hodge structures of the cohomology of the special fiber. Okay, so as far as the special fiber is concerned, it looks like the tensor product of what should be the cohomology of the two factors y and z. And second, the Kähler-Einstein metric on the special fiber similarly splits with respect to the splitting of cohomology. In particular, the sort of the cohomology class of this metric splits, sort of respects the splitting of the cohomology. So this, requires some care. This is probably the most subtle part of this argument. You have to actually get into what the Kähler-Einstein metric looks like and what its properties are. Very sort of naively, the point is that this is true on sort of the nearby fibers, and because these sort of Kähler-Einstein metrics have nice potentials, it makes sense to sort of take their limit in a locally trivial family. So it's sort of crucial that we're taking a locally trivial family. Okay, so now that's good news, because what this is essentially saying is that, so let me again draw a picture. So we have the disk, and we have we have this family, and over this puncture disk, it looks like a product. And then we have the special fiber. Okay, and sort of we have a nice family of Kähler-Einstein metrics, which over here, the Kähler-Einstein metric sort of splits into something that looks like the pullback of the Kähler-Einstein metric from the first factor, plus the pullback of the Kähler-Einstein metric from the second factor. And sort of putting these two pieces together, it means that X naught also has a decomposition of its cohomology such that the Kähler-Einstein metric splits into two semi-positive forms, omega 1 and omega 2. Because that's sort of and each of these guys is sort of coming from the correct sort of Kunith components of the sort of decomposition we get just by taking the limit of the Kunith decomposition. Okay, so maybe it's not clear why we want this, but the point now, for example, is that we can show that intersections necessarily have zero volume. Okay, so why is that? Well, if I look at, so remember on the special fiber, I've now gotten a splitting of the Kähler-Einstein metric into two pieces. And the point is, if I look at a limit leaf sort of in one direction, F, and look at the limit leaf in the other direction, let's call it G, well, the omega, the integral of omega, how to say, the volume of F with respect to omega 2 is 0. And likewise, the volume of G with respect, or even better than that, the sort of restriction of this form to omega 2 restricted to F is 0. And likewise, the restriction of this first form to G is 0. So if I have an intersection, a positive dimensional intersection, the restriction of both of these forms is 0. So the restriction of the Kähler form is 0, which is a contradiction. Okay, so the intersections can only be 0 dimensional. And likewise, by Kunith, if one of the limit leaves sort of splits into two components, it's necessarily the case that the new component has zero volume by sort of a similar argument. So that's also a contradiction. So therefore, what we can conclude is that these limit leaves sort of can only intersect in a zero-dimensional way, and they must continue to be irreducible in the special fiber. And it turns out that this is enough in order to get that they induce a splitting. Okay, so that that completes the proof of the decomposition theorem, and that also completes my talk. So thanks.